Hi everyone, I'm Yu Yue, and join me are my teammates Izemo and Zhang Jie. Our topic is the clash between mathematical ideals and engineering in CAN design, a deep dive into how math and real-world constraints shape the ordinary dream CAN. First, here is a quick look at our agenda, which is divided into three key sections as shown on the screen. Now, before we get into the formulas, I want you to recall a common daily scene. On a scorched summer day, you grab a 330 milliliter can of ice cola from a supermarket freezer. You probably only care about the refreshing taste, but have you ever looked closely at its shape? Standard cans are roughly 12.3 cm tall and 6.6 cm in diameter. This tall and slim look is everywhere, but a mathematician would look at this and tell you, this shape is actually not scientific. In an ideal mathematical model, if we want to use the least amount of aluminum to hold 330 milliliter, the optimal solution derived from differentiation is simple. The height should equal the diameter. In other words, the can should look short and squat, almost like a cube, rather than the slim shape we see today. So, here is a big question. If math says short and squat is optimal, why does every manufacturer choose tall and slim? Do this global company not understand calculus? Are they intentional wasting material cost? Of course not. To solve this puzzle, we have to look beyond the freezer and into the factory production line. In the real world, abstract formulas must survive manufacturing hard constraints. Next, let's move into Chapter 1 to see how the ideal model gets its first reality check when it meets manufacturing losses.
Hello everyone, my name is Izemo. If we assume a soda can is a perfect cylinder with a fixed volume V, our goal from a material saving perspective is to minimize its surface area S. The surface area consists of two circular bases and a sidewall. S equals 2 pi r squared plus 2 pi rh. By substituting the volume formula, we express the surface area as a function of the radius. S of r equals 2 pi r squared plus 2v over r. To find the minimum, we take the derivative and set it to 0. S prime of r equals 4 pi r minus 2v over r squared equals 0. By solving this derivative and substituting back the volume formula, we easily find that h equals 2r. Therefore, from a purely mathematical standpoint, the most material efficient design is when the height of cylinder equals its diameter. However, reality quickly shatters this perfect hypothesis. Take a look at a skull cane. It is about 12.3 centimeters tall with a diameter of only 6.6 centimeters. This gives us a height to diameter ratio of approximately 1.86. This means the real-world can is nearly 86% taller and slimmer than our theoretical ideal. Is that math wrong? Certainly not. We simply overlook the actual cost of engineering. In real manufacturing, the top and bottom of the can are not just formed out of thin air. They are punched out as circular blanks from large metal sheets. This introduces a critical engineering constraint: material waste. Let's define eta as the material utilization rate when cutting a circle of radius r from the sheet. Eta depends on how the circles are arranged. A square packing gives an eta of pi over 4, or about 0.785. And hexagonal packing, the most efficient way to tile a plan, gives an eta of pi over 2 times the square root of 3, or about 0.907. At this point, the actual material consumed for each circular blank is pi r squared divided by eta. Considering both the top and the bottom, our corrected total material consumption becomes S actual equals 2 pi r squared over eta plus 2 pi rh. With the volume constraints remaining the same, we substitute and get the function S actual of r equals 2 pi r squared over eta plus 2v over r. Taking the derivative and setting it to 0, S prime actual of r equals 4 pi r over eta minus 2v over r squared equals 0. Solving this gives us 2 pi r cubed over eta equals v. By substituting v equals pi r squared h, we arrive at the corrected optimal ratio, h equals 2r divided by eta. If we use square packing, where eta is approximately 0.785, the height to diameter ratio becomes roughly 1.27. As we can see, material waste from cutting is only the tip of the iceberg. To understand where the remaining discrepancy comes from, we need to shift our focus from geometric arrangement to significant manufacturing processing, such as the vertical side seam.
Hello everyone, my name is Zhang Jie. My student ID is AIT2509056. In this group assignment, I am responsible for manufacturing, depth correction, the cost of the seam, and the weapon for tough problems, Newton's method. Now let's get started. In actual engineering, the side aluminum sheet must overlap by a width W to be welded securely. This seemingly insignificant 0.5 cm overlap transforms the area function into a complex quantic equation. 4 pi squared r to the fourth minus 2 pi vr minus 2wv equals 0. At this stage, simple differentiation cannot yield the direct answer because the presence of W renders the perfect analytical solution invalid. So now what should we do? To face this unsolvable equation, we introduce a powerful tool from numerical analysis, the Newton-Raphson method. Starting with an empirical guess of RO is equal to 3.5, the first rotation radius becomes 3.48, and the second rotation narrows to 3.788, and the third rotation logs in at 3.7867. And just 3 rotations will obtain a higher precision optimal radius. Interestingly, the calculation shows that after considering welding loss, the can should actually become shorter and fatter. This indicates that material saving is not the only driving force behind the solder can shape. Why is reality slender? Why do manufacturers risk waste at material to make the can slender? The answer lies in physics and psychology. According to Newton's law of cooling, an object's cooling rate depends on its specific surface area. A slender can has a larger surface area relates to its volume, meaning it chills faster in the fridge, a vital feature for selling cold drinks. And a diameter of 6.6 cm is ideal for the human hand to grip consumer. Psychology. Slender packaging often creates a virile illusion of greater volume, and for logists, standardization requirements for cell space and vending machines. In conclusion, through this exploration, we see that mathematics provides the bottom line for costing engineering design. However, the final shape of an industrial product is determined by a complex, multidimensional game played between manufacturing, physics, human-computer interactions, and business strategy. It is this interplay that gives cold industrial products their final soul. That's all my report. Thanks for watching and listening.